Hello, I'm Bill Leipold, and welcome to this edition of Breakfast at the Barracks. Joining me is Charles Keeton, Professor of Physics and Astronomy at Rutgers, New Brunswick. Chuck, welcome to the show.
Thank you. It's great to be here.
I want to start out by saying you won a presidential award for science and engineering, a huge accomplishment. Can you tell us a little bit about the research and kind of how it got you to that kind of award?
Well, let me first mention that the award actually was through a program sponsored by the National Science Foundation to integrate research and teaching. So that was, it was kind of a nice pat on the back to know that the research is recognized, the interest in education as well. So on the research front, I've been, for a number of years, studying how gravity bends light and using that to investigate the idea that galaxies are embedded in enormous halos of dark matter.
Okay.
There's growing evidence for this dark matter throughout the universe, and we have an increasing understanding about what the dark matter is, but there's still a lot of mysteries. So there's been a lot of evidence recently that the dark matter can actually clump together on small scales. So a galaxy like our own Milky Way should be surrounded by thousands of dwarf galaxies that are all but invisible. We can't see them with our telescopes, but if they're there, they affect how light bends.
So let's draw back.
Yes.
Because I want to make sure, you said a whole bunch, and I'm trying to figure it out. So the first thing is, you make light bend. You kind of researched in terms of how light bends, so can you explain a little bit more to me about that?
So this goes back to Einstein's general theory of relativity. And Einstein taught us that we should think about gravity in terms of the curvature of space-time. So people like to use the analogy of a rubber sheet. So you take a rubber sheet and stretch it out tight, and you roll a marble across it. What's it going to do? It's going to roll in a straight line, which is a manifestation of Newton's first law, which is that an object in motion will tend to stay in motion in a straight line. But what Einstein told us is if there's a source of gravity, if you put a bowling ball on that rubber sheet, it's going to distort the rubber sheet. Now you rolled a marble on the rubber sheet, it's not going to go in a straight line anymore. It's going to roll down the hill a little bit. If you don't roll it very fast, it's going to actually roll down and hit the bowling ball. And that's like you throw a ball and it falls to the earth. If you roll it fast enough, it'll skirt by the bowling ball, but it'll fall down the hill of the valley a little bit and then come out the other side. But it will come out in a different direction.
So it kind of curves and kind of S's over.
Exactly. Well, it's not so much an S, it's more like a coming out and then just bending, deflecting in this direction.
All right. And so that would hold true for light then?
And that's what light does. So essentially light wants to take we say the shortest path, what we really mean is the fastest path. It wants to get from here to there as quickly as possible. And on a curved surface, the fastest path might actually be a curved path itself. Another way to think about this is airplanes. So if Continental now flies from Newark to Beijing. If you look at an atlas, open it up flat, Newark and Beijing are about the same latitude. So it looks like you just fly due west, straight line, you get to Beijing. But if you actually take that flight, where do you go? You go over the North Pole.
Well, I was going to ask the question because I've been on that flight before. We go over the North Pole, and I'm like, why are we going over the North Pole and not this way?
So you think, why do you go over the North Pole? It's because the Earth is curved. And the shortest distance between 2 points on a curved surface will usually be a curved path. And so that's basically exactly what light is doing in a gravitational field.
So let me ask this question. So I'm looking out at the stars. I see lots of light coming in. You're telling me that when that light comes in and it passes a potential, whether it's a potential planet, a potential moon, that there's gravity focusing on that, and it's just not a beam coming straight in.
That's correct. Now, most of the time, it's a very small effect. So we don't even notice it. So Einstein calculated that if light passes right by the surface of the sun, it would bend by a certain amount, which is about 1,000 times smaller than the diameter of the moon. So it's a very small effect. It's measurable, but it's a small effect. So most of the time, you look out at the sky, and that light is all fine. It hasn't been distorted. But if you can get a situation where you've got a source of light directly behind a strong source of gravity, such as a galaxy, then if you've got that very good alignment, you can actually get the light which comes around both sides of the galaxy. So when we look out, we see light coming, what appears to be the same light coming from two different directions. So it looks to us like there are two copies of the same source on either side of the galaxy. And we can use the two copies of the two images of the source to figure out how the light bent, and then that tells us about the gravitational field of the galaxy.
I also want to talk about the word galaxy, because when I hear the galaxy kind of context, I think of our Milky Way. And you said that there are multiple galaxies out there originally. So
billions and billions, as Carl Sagan used to say.
So when we're talking about this, you also talked about the conversation of dark matter.
Yes.
What is that?
What is that? That's the million-dollar question.
All right.
So what we know about dark matter is either a little or a lot, depending on your perspective. So in some sense, it's very humbling to discover that everything that we know about, all the matter in this room, all the matter that anything that people have studied with chemistry, biology, let alone social sciences or humanities, that's really just the tip of the iceberg. Even when we point our telescopes out at the universe, we're, again, literally only seeing the tip of the iceberg. We've deduced that there's about 5 times as much dark matter out there as normal matter, the matter that we're familiar with. So what is this dark matter?
I was going to ask that question because I understand the matter part. I'm trying to understand. Okay.
So as far as we know, it's something that exerts gravity and doesn't do a lot else. So we detect its presence through its gravitational influence. It influences how galaxies form and move. But what is it? Well, all the evidence points to it being some sort of exotic particle. It's like a fundamental particle like a proton or a neutron or electron, but different, something that we haven't encountered yet. And so, in fact, there's dark matter everywhere. There's dark matter in this room. It's flying through this room as we speak. So but it doesn't really do anything except exert gravity. It does not interact with light, and probably, if it interacts with other matter at all, it's very, very weakly. So most of the time, it just flies right through us. We don't even notice. But if it's there, it exerts gravity, and astrophysically, we can infer its presence from the gravity. If it's flying through this room at the moment, then we may also be able to catch it, and there are physics experiments going around the world trying to catch the dark matter as well.
All right, I'm going to go back to my high school physics class. So I got to see what a proton looked like with the negatives and the positives. I got to see all that kind of other stuff. What's the physical kind of context of dark matter, and how do we know it's there? Because you talked about we don't know how much it's there, but we've calculated X, Y, and Z to be able to say it's so much. So I'm trying to figure out how a student might understand that, or how I might even understand that.
They're sort of taking two prongs here. So one is the astrophysics. We figure out how much stuff is out there from its gravity. In that case, we historically have been able to say very little about what the particle or what the stuff actually is.
Okay.
All we know is where it is, how much there is, how it's distributed, which is a fair amount given that we haven't ever seen it.
Right.
But still, we don't know what it is. From the particle physics standpoint, we can say, okay, we know what protons are like. We know what neutrons, we know what electrons, other particles that the Large Hadron Collider is producing and studying, for example. Mm-hmm. So there are theoretical reasons to believe that other types of particles might exist. And in fact, the LHC Large Hadron Collider is looking for these other kinds of particles, the Higgs boson among others. Right. So it would be a particle, by the best theories that we have today, it would weigh something like several hundred times the mass of a proton. So it's bigger than a proton. Right. And it doesn't have charge like a proton does. So you mentioned protons positive, electrons negative, neutrons are neutral. If it had charge, we would know about it because of the electric force.
But
so it must not have charge. If it had charge, it would also interact with light. Then it wouldn't be dark.
Okay.
So
I didn't know that. Okay, that's good. All right.
So it is, in fact, through the electric force, the electromagnetic force, that particles interact with light. So if they have an electric charge, they will interact with light.
So then the question's going to be, if we know the dark matter exists, and we know it exists in large context, how does one study it if they can't see it?
That's where, for me, gravitational lensing, the bending of light by gravity, comes in. Because if it's there in a galaxy, so I look at a distant galaxy, and again, all of the historical evidence points to galaxies being embedded in huge halos of dark matter. Mm-hmm. So if there's a huge amount of dark matter, a huge collection of dark matter around the galaxy, it will affect the gravitational field and therefore affect how the light is bent when it passes by the galaxy. So if we can observe the light bending, we can deduce that the dark matter is there even if we can't see it, because our telescopes are not going to detect the dark matter directly. So
I'm going to ask this question, because this is a question I think that our viewers might have. How does one become interested in the idea of bent light, dark matter in space? How did it become interesting for you, and when did you know that's what you wanted to study?
For me, I think the formative years were 1979, 80, 81, when I was 7, 8, 9 years old. That was the time when the Voyager probes were sending back the first amazing pictures of Jupiter and Saturn. There was also the start of the space shuttle program. And it was that confluence of events that really, as an impressionable 7, 8, 9-year-old boy, I saw those and I thought, wow, that is really amazing. That's really cool. We can study these things. Right. And after that, I just tried to read more and more. My parents were very supportive. They bought a telescope. Mm-hmm. My teachers were very supportive. And I feel fortunate to have had such great support all through those years. And this really comes to hit home for me right now because my son is now 8 years old. Okay. And so I'm realizing that I'm now living the dream that I had when I was his age. Wow. And I think that's really pretty special.
That's amazing. Besides your research, you also won the award for the conversation around teaching. So it was teaching and research. So explain to me, I know you kind of have a passion for teaching, so explain to me where that came from.
I think for me it all starts with a passion for the material. I think the universe is a fascinating place, and I can't help talking about it. Okay. I want to tell people what I find so exciting, what I find so interesting, and just communicate to people. Astronomy is a great field for generating interest, and a lot of people are fascinated by the universe. But there are a couple of other factors. I once heard a prominent cosmologist asked, why should we as a society spend money on astronomy when there are so many other pressing problems? Poverty, hunger, climate change, right. what have you. And he said that for him, it really comes down, the value of astronomy comes down to 3 words. We do wow.
You do wow.
And I thought, that's it. For me, it really does come down to we do wow. I say, wow, look at this. I want to stand up and say, wow, look at this, wow, look at that. Isn't this amazing? Isn't this wonderful? But I think more than just the fun element, there's also a practical value to the we do wow, to the wow factor. Because I think that a lot of the challenges that our society face require scientific literacy and critical thinking skills. And I see astronomy as a way to open the door, as a way to invite people to that conversation, to draw them in with a wow factor, and then use the astronomy to say, look, here's how we reason based on evidence. Right. Here's how we deal with imperfect knowledge and limited knowledge. Here's how we evaluate arguments. Here's how we critique ideas without criticizing people. We do all those things in science. Astronomy is a vehicle for communicating that. And I'm not setting out to turn all my students into astronomy majors, but I do hope that they become scientifically literate citizens.
One of the things you talked about was that the challenges of NASA, conversations around space probes, all those kind of things really excited you when you were younger. And that wow factor was there for you in terms of being able to do that.
Yes.
We've just ended the whole space shuttle kind of context, and we don't have a plan, or NASA hasn't explained a plan. So what do you think is going to be next for us nationally in terms of gaining interest in the idea of astronomy and physics?
So yes, the space shuttle program just ended, but the unmanned space program is still going strong. Was it yesterday? Just recently, NASA launched the Curiosity probe to go to Mars. Right. So that Mars has been a wonderful target of lots of missions, and we now know almost as much about the geology of Mars as we do about the geology of Earth, which I think is another amazing topic. So the unmanned space program, the spirit of exploration still lives on. I think that the manned program, the manned spaceflight, human spaceflight, certainly has an attraction that the unmanned probes don't provide. So I'm certainly interested in how that turns out. But again, going to Mars, recently the Juno mission was launched to Jupiter. The Cassini mission is still going strong around Saturn. There are many more deep space probes looking at galaxies and other distant objects. So I think that is all alive and well. And NASA has done a very good job of drawing on the wow factor to communicate to the general public and sustain that interest. So I think that's all very positive.
Well, let me tell you, I think you're doing some great work. And I love the fact that you broke this down so even somebody like me who's not a science person can get it. So I appreciate that.
Thank you.
Thanks for being on the show. Hopefully we'll have you back sometime soon.
My pleasure.
We'll be back with you in a second. Welcome back. Joining me is Mauricio Delgado, Professor of Psychology at Rutgers, Newark. Mauricio, welcome to the show.
Thank you for having me.
Your research focuses on emotions and the brain. What I perceive to be 2 big words, so why don't you two big concepts, so why don't you help us to understand what your research is about?
Well, so our research is motivated by a simple observation that our behaviors, the decisions that we make, the choices we make, are influenced by positive and negative forces in the environment. Okay. So what that means is actions that lead to positive consequences tend to be repeated. So these positive consequences are rewards. They put us in a positive emotional state. While actions that lead to negative consequences tend to be avoided. These are punishments, things that put us in a negative emotional state. In the lab, what we're interested in is how the human brain learns about these positive and negative reinforcers, how it assigns values to different rewards and different punishments so we can make comparisons, and how it uses this information to then make decisions.
So let me ask you a question, because the minute you say all that,
Yeah.
I think of parenting. I think of hot stove, go to touch it, conversation of ouch, it hurts, kind of reinforcement of somebody yelling at you, those kind of things. Is that kind of what we're talking about in some ways?
Yes, yes and no. It's how we learn through life what's positive and what's negative, so we can apply it to many different contexts. It can be as simple as learning that something, if you're thirsty, the water fountain predicts water.
Okay.
Or avoid the hot oven, as you said. But it goes a little further than that, because it becomes important later on as you start to value different kinds of rewards and different kinds of punishments, because if you tend to overvalue a reward or a punishment, you might make bad decisions.
Okay.
This is the case of drug-seeking behaviors in drug addiction, for example. So the other part of our research program that we're really interested in is how does the brain learn to exert control over the excessive positive or negative emotion reactions that we may have to some of these stimuli.
So let's take the addiction for context.
Okay.
Somebody who eats for emotional relief, somebody who goes shopping for that high to be able to deal with some stress at work.
That's right.
Those kind of things, those are some of those positive
Correct.
emotions that you kind of study.
And initially they can be positive, as you said, they can be some escape, so they can be something that a person enjoy. But at times, if we end up doing it too much, then it becomes a problem, because we tend to maybe overdo it and bypass natural rewards that we have to take. So for example, so you might shop too much, since you brought the example of shopping, at the expense of using that money for things that you usually have to do. So you have to buy food and water for your survival. Instead, you're excessively making bad decisions and impulsively shopping. So we try to understand the brain circuits involved in learning what's positive and what's negative, but then if we tend to overweigh the positive, how can we control ourselves in the case of the shopping? So we put everything into context and try to shop less or eat less bad food and make better decisions.
You talked a little bit at the beginning, it's based upon observation, but is it only observation, or is it observation of physical features, or is it observation of some other kind?
Well, we tend to characterize the behavior first, so we try to understand how the person makes these kind of decisions, or how do they respond to this through observation or subjectively, but more importantly, we rely on a tool called functional magnetic resonance imaging, which allows us to peek inside one's brain. Okay. And that way we try to understand what particular areas of the brain are going to be working or necessary when you're learning about these types of reinforcers, and essentially when you're learning how to control your emotional responses to these reinforcers. Knowledge of these brain circuits allows us to try to make better predictions about how an individual may adapt in the future in terms of their decisions. Because
I think I'm a little ignorant in this area, it sounds to me like there's some neuropsychology here, there's some biology here,
right.
So you need to know what part of the brain's in charge of what. And
Correct.
then you need to be able to, when you say do the microimaging, or be able to understand what part of the brain is stimulated
Correct.
by the activity.
Yeah, so it's a nice combination of biology and psychology, okay. Which is the field of neuroscience, and specifically cognitive neuroscience, because we get to understand how the brain enables the mind. So essentially, how does the brain allow some of these cognitive thoughts of ours and our behaviors and psychological observations to happen. In its simplest forms, we just put somebody in an MRI scanner, and we look at how the blood flows into certain parts of the brain when they're doing simple tasks such as finger tapping, to what we do, which is usually have people react to an emotional outcome. So receiving a reward, receiving a punishment.
So when you're doing that in an MRI, how does it happen? Does that happen with regards to pain? Does that happen with regards to, okay, now here's a credit card for $500, go shopping? How does that happen?
Yeah, it's a lot more fun than finger tapping, I'll tell you that.
All right.
I'll give you one of our basic experiments is we bring people to the MRI, we bring people to the Rutgers University Brain Imaging Center, actually, and we train them on the experiment, and this simple experiment is a gambling game. Okay. Because we want to see how people respond to winning and losing to positive and negative reinforcers. So we have them lie in the scanner while they're playing this game, much like a slot machine in Vegas, except we have better odds.
All right.
And they either win or they lose, and we specifically look at which part of the brain is activated, where is the blood rushing to that part of the brain when you win versus when you lose. Okay. So now we can identify these particular areas of the brain. They're associated with positive feelings associated with winning, negative feelings associated with losing. And we can do different kinds of experiments there to try to understand what happens if you change the type of game, what happens if you make it a little riskier, what happens if people try to make risks or try to take risks to get those rewards and punishments. So we get to understand a little bit more about risky decisions.
Well, I was going to ask the question, because part of, I think, what we all experienced, especially near Atlantic City or Vegas, is the conversation that we're up 200, but we're going to spend it down to what we put into the machine, and then you try to win it back. So does it kind of, do you kind of measure some of that thought process or
we do
simulation process?
We try to understand why do people make decisions that they make, right? So besides just going to the brain response to this reward, is what happens in your thought process when you're now trying to make that kind of decision, why you're chasing a loss, or you're aware of the fact that the odds are really against you, but yet you're willing to overspend your endowment or however much money you have to seek that reward. So the argument here is that if we know the brain circuits involved in these psychological processes, we have a better idea of how to perhaps help these people train their brains, and eventually that will be relayed or be shown in the behavior as in better decisions.
So let's talk about this for a second, because we're talking about scanning, you're talking about MRIs and kind of looking at the brain stimulus. Are there interviews or conversations with the folks afterwards to kind of see how it matches up, or on occasion how sometimes it doesn't match up?
Oh yes, definitely, especially when we're doing these kind of emotional research. You can't just rely on an experiment. Being in an MRI is anxious as it is. You're kind of in a tight space. You might be doing an experiment I described to you. You might be playing a game with monetary rewards, but it's not quite the same as if you're really in the environment of a casino. So it's very important for us to actually talk to the person afterwards and even before, and try to understand any personality characteristics that may drive the behavior a little differently compared to other subjects or other people that we may have in the experiment. How their experience was of the game. Maybe they were completely bored. Maybe they didn't believe us at all that they were going to get money. So all these psychological factors certainly play a role when we're trying to understand what's going on.
One of the things that you talked about was the fact that it's an MRI, so it doesn't have the music, it doesn't have the smells, the sounds.
That's right.
One of those kind of things that when I go to Vegas or I think of Atlantic City, I think of the slot sounds, or I think of all the images around me. So how do you kind of replicate some of that along with the kind of...
Yeah, it's certainly hard. We try to make it as close to as possible. I think that we refer to those type of stimuli as conditioned stimuli. And you know it very well from when you go to Vegas, you see a slot machine. For somebody that might lead to the impulsive decision to go gamble right away, or the sounds or the smell, may it be. So we sometimes have experiments where we actually have, instead of just simple stimuli in the screen, we have slot machines. We have pictures of things that are more commonly associated with the risky behaviors. And we measure then the brain responses to that conditioned stimulus. That leads to that craving feeling of, I want to gamble, or I want that potential reward. And we actually pay out pretty nicely comparatively. So we try to make the environment as close to as possible. And we get the behavior that we wish for. The interesting part is what we're really trying to do is trying to control people's responses to these conditioned stimuli. So if you are, a little bit sensitive to the conditioned stimulus, so if you see the machine, technically you're going to want to gamble. Can you control that impulse? Can you control that emotional reaction and then reduce the chance that you are going to make that risky decision?
So in terms of the reduction, so the reality is you're not just studying how the brain, but it's really about the impulse too. Can you control the impulse? How is it that you control that impulse? So we're really talking about some ways in terms of methods also.
Correct. So, and then I have two answers to that. One is that at least maybe that's me, I think it always comes back to the brain. Because if we have one brain area that's involved in that emotional response, that conditioned response to the potential reward, we have a different brain area. That's the executive control that's going to say, please tone that down. Let's not make this mistake. So these brain areas are talking to each other, and sometimes one wins, sometimes the other one wins. What we've been trying to do is come up with strategies that people can use to try to decrease their emotional reaction, and with the hope that that will lead to less impulsive decision making. So we have people thinking about different things that make them a little less emotional, for example.
So talk to me, I know one of the things that you're really good at is relationships with students and working with students. So talk to me about how students are really a key part of your lab.
Well, so pretty much all the work in my lab is done I get to talk about it and I get the benefits, but it's really done by all the students, the great students I've had a pleasure of working with. And myself, I've been very fortunate to have worked with great mentors over my career. So I now get to give that back to my students, and it's a pleasure to see them grow as scientists and as individuals and move on with their careers. I actually had a lot of students graduate this year, and they're moving on to bigger and better things in terms of their careers, and it's really nice to see.
Well, let's talk about that. Last year was a big year for you. You won a major award, got to meet the president, so why don't you talk a little bit about that experience for us?
It was an incredible honor. I was very happy and humbled to be in that position, and I'm very thankful to all the mentors and the students that I've had to help me get there. And it was just a great experience to be able to win this award and meet the president and actually shake the president's hand.
So why don't you give us a little background about what the award is? So
the award is the Presidential Early Career Award. It's for the contributions that some of the work that me and my colleagues have done over my career. And specifically, the focus on it is on using these regulation strategies or these control strategies that I was referring to you about on how to control these emotional reactions so we don't make risky decisions. And this is one that the National Institute of Drug Abuse was particularly keen on.
Oh, wow.
And so we've been learning how we can use these techniques to train brain circuits to decrease our emotional reactions.
Let's talk about this too. It's really an NSF award, a National Science Foundation award, that quite candidly you apply for the grant. It's based upon your research and your grants awards that literally there are thousands of people, thousands of professors who turn in National Science Foundation grants applications, get awarded, turn in their final grant analysis, and you were chosen based upon your work, what you do, and it was one of those things that you were just excited to get an NSF grant.
That's right. I was
excited then to turn in your information and then to be chosen as one of the winners of this major award is a huge honor.
It was an incredible honor, and was, as you said, and mine was actually through NIH, National Institute of Health. And the National Institute of Drug Abuse specifically, and I was just ecstatic of even being able to get the funding for the research, and I got very good feedback on the grant. And when the news came that, on top of it, I had gotten the award and the chance to meet the president, I was just floored and completely honored and very grateful for everything that has happened to me and all the people I've worked with to be able to get to that position.
It is well-deserved for you and is well-deserved for your students, and good luck with everything, and hopefully we'll have you back on the show soon.
Thank you very much for having me.
And thanks for being here. I appreciate it.
Yeah, it's a pleasure. Thanks.
Well, that's all we have time for this edition of Breakfast at the Barracks. For more information about any of the subjects we've discussed here today, please visit our website at rutgers.tv. For all of us at Rutgers Division of Continuing Studies, I'm Bill Leipold, and thanks for watching.